Okay, everybody, welcome to class. Limited numbers, people are traveling. 1/6 of our country is traveling for this holiday. It's pretty crazy. 50 million Americans are traveling for this holiday. Pretty wild. And it just happens to coincide with Stormageddon, which is rolling in. We'll see what that does to travel. In any case, thanks for coming today. We will go over anything you want today. Maybe what we should start out with is turn to the person next to you and list 2 or 3 for each one of these questions, but what topics have been the most challenging, and then what questions are you most worried about showing up on the final? Discuss that with your neighbor, and then we're going to work through examples of those things. Okay, what comes to mind as you brainstorm this? What topics were the most challenging? What things are you worried about showing up on the final? Yeah, Pramit? Phase diagrams. Another vote for that. Another vote. Chase, what do you think?
I think, the phase diagrams, labeling it with like just starting from liquid and then primarily combinations, but then also like on the first midterm, looking at that cross section and then being able to identify like what is what phase that you gave us on that cross section.
So from an actual material microstructure, okay. Going from microstructure to phase diagram understanding. Okay, what else? Surely that can't be all that was challenging. Creep? Creep is almost for sure going to be something I put on the final because I didn't put it on midterm, was it 2 or 3? There was too much to cover, and so I didn't cover it, so it's very likely going to show up on the final. Creep? What else? Yeah?
Manipulating equations to like graph them and then extrapolating data from those graphs using natural law on one axis versus another variable.
Yep, fair enough. The whole class? The whole class? We're going to do a very efficient review of the whole class. So I haven't written the final. I'm writing it now. What I am going to do is I'm going to show you the last 4 or 5 finals from this class, and you can see what typically is on it. It will be typical, what I'm going to do this year. Yeah, Lennon? Yeah. Once the study guide is up, then I will hold a separate review. So if you want specific worked examples on something, we can do that. Yeah, Josh? I don't think so. I think that is a benefit of coming to class. I will YouTube record this, and so you can watch it again on YouTube, I guess. But I'm not going to post them. Okay? Some of the questions you'll have seen before. Homework questions are old exam questions for the most part, right? Other things that you'd love to make sure that we cover today? Yeah. Okay. Anything else? Yeah. Anything in particular? There's a lot there. We did band diagrams, we did doping, we did conductivity of semiconductors, temperature dependence, mobility. There was a lot there. Okay. Yeah.
I think we could go over a few things that you noticed everyone seemed to do poorly on any of the previous midterms.
Yeah. Yeah, I have to think of what things people did particularly bad on. It was kind of all over the place. Yeah. Drawing cubes. A cube drawing workshop. Andrew's willing to host it. Okay, let's start with this. First, let me show you some previous exams, and then we will work through some examples of things that look particularly terrifying. All right, so starting from last year, our final exam looked something like this. So the key, what I'd like you to do is imagine that you're taking the exam and think about how you would approach this problem. Don't start working it out if you don't want just yet, but think about, realistically, a typical time frame for these things is about 5 minutes per section, right? Per A and B. Now, something that's worth a lot more points is probably going to take more than 5 minutes. Like a creep problem is longer. It's maybe a 10-minute thing. But in general, you don't have a ton of time. So this exercise of thinking about how would you approach it is useful for you. So part A says the following. Part A says, turbine engines, which power airplanes and electric generators, have individual blades, which are all single crystals of nickel-based superalloy. The reason single crystals are used is because the blades operate under stress at high temperatures, and the designers are worried about creep. Why would single crystals be advantageous over polycrystalline materials when it comes to preventing creep, right? So this is a concept question. The final will certainly have a mixture of calculation and concepts. So you'd have to go back, and presumably you would have already reviewed creep because it would have been on the study guide, but you would have learned what things help and prevent creep. Here I've said single crystal is good to prevent creep, so why might that be the case, right? So it's a concept question, so not as much studying needed for that one in terms of how to work a problem, more it's fundamentals. Next one says, consider the creep information shown for the superalloy. Determine the steady state creep strain rate at this temperature and that stress. And I say note, do not try to read points off the plot. Instead, use the best fit equations. If you try and read them off this plot, it's easy to get it wrong, especially if they're plotted on natural log axes. Well, actually, these are actually linearized, but still, instead of reading points off the plot, I explicitly say to use the equations. I've given you best fits for both these things. On the plot on the left, you see the natural log of the creep strain rate. You know that because it's epsilon with the dot. That tells you it's a rate of strain, right? And then over here, you've got 1 over temperature. On the other hand, you've got the exact same thing, but it's natural log of stress as opposed to 1 over temperature. So what did I ask you? I said determine the steady state creep strain rate at some temperature and some stress, right? So if you look at this, you could try and figure out what the strain rate is, right? So these are all given at the same stress. It's all at 500 megapascal. So even if you found where 710 is on this plot, like 710 Celsius, you turn that into Kelvin, you take 1 over that, it's somewhere on this plot. You couldn't just read it off this line. How come? Why could you not just read it off that line? Right, but all right, let's assume that you could read it off that line. That gives you the natural log of the strain rate, so you could take exponent of that and get the strain rate. Why is that not the right answer, though? What's wrong with that approach? So what factors can affect strain rate? Let's jump over here and write it up. So steady state creep strain rate, which will almost certainly be on the final, looks like this. K, a constant, multiplied by our stress raised to an exponent n, multiplied by the exponential of an activation energy for creep divided by your thermal energy, kBT or RT. Okay? Or in other words, the creep strain rate that you observe, epsilon dot, is a function of lots of different things. This is a constant, n is a constant, but you've got 3 things that you can change. You've got the stress, the temperature, and the activation energy. So from that plot that you just saw, think of what it gives you. This gives you the strain rate as a function of temperature, right? And this is all happening at a specific stress, right? So even if you figure out the slope of this thing, this all corresponds to 500 megapascal stress. The question's asking you to figure out at 710. So even if you read off this plot, this wouldn't give you the right answer because it's not the same stress. So we need to figure out the stress dependence, basically. We need to solve for this exponent of how stress influences creep, right? So you're going to have to do 2 equations and 2 unknowns. To answer that, now come over here. This is all at the same temperature, and it's not the temperature that we want. It's not 710 Celsius. It's 873 Kelvin, right? But this gives you the effect of stress. So you're going to be able to write 2 equations and 2 unknowns to solve for both the activation energy, which is related to temperature, right? Q sub C, you're going to get that from this plot, and you're going to be able to solve for n from this plot. So the question is how, right? This goes to one of the questions we had, which is how do you linearize these types of equations? Well, think what's plotted. Let's do the first one first. The first one shows natural log of strain rate against 1 over temperature. So let's go ahead and transform this equation to look like that. the first thing we might choose to do is let's take natural log of both sides, right? Or if you want, you can bring this stuff over first. It'll make it a little easier. Let's bring it over. So now we've got epsilon dot over k sigma n equals exponential of negative qc over kbt. Now when we take natural log of both sides, it's pretty straightforward. You have natural log of this minus the natural log of k sigma n equals negative qc over kbt. Right? We can further separate this thing out, this expression down here. But right now, we know that it's all a constant because for this equation on the left, these are all at 500 megapascals. So sigma is a constant right now for us. It's not changing. Okay? So this whole thing is just a number. Okay? What is changing, right, is that this is plotted against 1 over temperature. So the slope of this thing on the left is negative qc over kb, or r, depending on whether you want your activation energy be in a per atom or a per mole basis. It's totally the same. Okay? Any questions so far on that step? So to do that, you would then look at this equation and the slope's given. So that negative 66,150, that's equal to the activation energy divided by kb or r. I would probably make it clear which one you should use because I think that would change this answer here. I probably needed to say whether it was kb or r. I think that they use r for creep. I have to look back in my notes. When we go back to mechanical properties, I think it was actually under failure we talked about this. Creep, it's probably r, but let me just double check. Okay, creep is given in r. Okay, that makes it clear. It's typically done in r instead of kbt. So the slope would be negative q over r. Okay? Any questions so far on that? Oh, yep. Is this gone? Oh, I got to scroll up for it. Right here. All I've done is I've separated that, right? The term that I held together before, I broke it out here. It used to be k multiplied by sigma to the n. When you can separate that, property of natural log means you can bring that exponent down and it's now multiplied by that. But it's mathematically identical. Okay? Any questions so far on this? No? So now let's look at our other equation. This one plotted the strain rate against natural log of sigma, right? So this is now the thing that's changing. This is x, natural log of the stress. So if we go back to this equation, which we were just at, this is now x, right? This natural log of sigma. This is just a constant because temperature is now the same. So this is just some number, right? This is just some number, right? So you can figure out from the slope what n should be. N is now going to be your slope. So over here, n is a positive number. It's equal to 20 in this case. Okay? So does this make sense how you'd at least go about approaching one of these problems? As always, on all of my exams, if you look at any of the exams I've given, we always have a very generous rubric where I give out typically half the points just for knowing the equations and setting up basic ideas. Like take a look at this one. This was some battery problem. The rubric said, okay, correct direction of equations, right, is worth 2 points. Correct coefficients for the equation. Just by balancing it, you got 2 points. And then correct sum, if you add them up, it's worth the final point. Like the final math is typically not worth much points on these. I give you most of your points for setting things up, which means if you're crunched for time, it's much more important that you realize what the question's asking and set it up. And if you don't have time to solve it, then you don't have time to solve it. But that's not going to be the majority of your points. It'll be a smaller fraction of your points. Any questions? So you would, from this graph, obtain the value of q. From this graph, you'd obtain the value of n. What's your next step? Well, you need to plug in a value because there's still one more variable we need if we go back to this. To solve for the strain rate at any given temperature and any given stress, once we know q and n, you can plug in stress, you can plug in temperature, but before we get a strain rate out of it, we need to solve for k. So once you know q and n, take a value from the plot for either of these scenarios, solve for k. Now you know k, n, and q. You can solve for any combination of stress or temperature. Okay? Can I answer any questions about this? Can I clarify it further? Okay, let's look at another one. All right, this later says, okay, a semiconductor company relies on diffusion to extrinsically dope otherwise stoichiometric gallium arsenide. Gallium arsenide, when we say it's stoichiometric, it just means it's pure, no dopants, right? If you choose to dope it, you're going to modify its electronic properties because it's a semiconductor. We're extrinsically doping it. It says a gallium substrate is initially doped with 10 to the 18 acceptors. If you sought to construct a Mosfet transistor, suggest an appropriate dopant for the source and drain regions. So on this one, it's going to be helpful to remember what is going on in a Mosfet. A Mosfet looks like this. You've got your silicon, or in this case it's gallium arsenide, is your base material. And it's initially doped with what? N-type or P-type? It says it's initially doped uniformly with 10 to the 18 acceptors. Is that N-type or P-type? They are accepting electrons. If they accept electrons, what do they do to your material? They create holes, right? The band diagram, if we drew the band diagram of this thing, acceptors live right here. Basically, you put lots of acceptors there so that these electrons can go up and occupy these acceptor sites and create holes in doing so, right? So this is a P-type dopant. We've P-type doped gallium arsenide because we've put holes in the valence band, which are now free to conduct, okay? A fair question, I don't know if I ask it, a question might be, what material would you dope it with to make it? To put these acceptors in it. I've just called them acceptors. What chemical might they be? To answer that question, you could look over here at your periodic table and you could say, okay, gallium arsenide is a 3,5. It's got a group 3 and a group 5 together. If you want something that's going to accept electrons, what's an example? If it's going to accept electrons, it better not have more electrons than the gallium and the arsenide. It should have fewer than either the gallium or the arsenide. So gallium, you could choose something to the left of it. I don't know if zinc is a good P-type dopant or not in gallium arsenide, but it's not a bad guess, right? One could imagine that it could pick up one more electron and start to look like gallium, right? Or on the other side, maybe on the arsenic side, you could put some silicon in. If the silicon chooses to sit on the arsenic site, it might act as an acceptor. This one's a little bit tricky because you could think maybe that silicon's going to sit on the gallium site and act as a donor, and I don't know which one it's going to be, right? But you could guess, okay? The question says, okay, what type of dopant should you use for the source and drain regions? Is what it's asking. So let's go back to our drawing of what's going on in a Mosfet. So this thing is gallium arsenide, and let's assume that it's zinc doped to start with. That's pretty unambiguous. It should P-type dope it, right? So how does a Mosfet work? Somebody remind me what's going on in a Mosfet? What are the key components? We know that there's a source and a drain because the problem just said it. Landon, what else?
There are some insulators to do something.
Yep.
Insulators.
We'll call this a source, and we'll call this a drain. Your insulator is going to live right here. Right? Then you've got a metal right there. So the reason they call this a Mosfet, it's a metal oxide semiconductor. So you've got metal oxide semiconductor, Mosfet. And then FET, it comes from field effect transistor. The field effect means when you put an electric field across this thing by applying a voltage between your substrate and this metal gate, you create, since this doesn't conduct electricity, we learned about parallel plate capacitors. You could imagine a scenario where you pile up negative charge here and positive charge here, right? And in doing so, this P-type material, which is normally full of positive, like it's normally just chock full of positive because it's P-type, you created a region which is now N-type, right at the skin of this thing, okay? So the question is asking, what type of dopant should you put in your source and drain regions? A Mosfet, by definition, the source and drain have to be doped opposite of what your bulk is doped. In this case, the bulk is doped P-type. So we need these to be N-type. So we could go back to our periodic table, and we could say N-type means it has extra electrons. It's donating electrons, right? So let's say the arsenic site, if we put something like sulfur or selenium on the arsenic site, we should be N-type doping it. So those would be appropriate dopants here, right? Now they've got an excess of negatives in there because we've doped them to have lots of negative carriers free electrons. What's slick about this is that you can now get conduction between the source and the drain, which is how these transistors work. But that conduction only occurs when you apply a gate voltage. If the gate voltage is not applied, then all of these negatives disappear, right? And instead, this is filled with positive. What happens when you try and pass electrons through this positive region? They recombine. You create an LED. None of that current gets through. The current only gets through when you apply a voltage across this gate, which gives you a little tiny channel of conduction, right? So in studying for this question, you would have wanted to go back and review how MOSFETs work. Think about how dopants work, okay? It says, okay, in a different silicon-based device, you seek to create p-type channels by doping a material with phosphorus. Let's make sure that that makes sense. Silicon's right here. Phosphorus is to the right. It's going to act as an electron donor, right? And I said, you seek to create p-type channels by doping a material with phosphorus. That's just wrong. That should be aluminum. I don't know if I actually published that or not. That's wrong, right? That should be n-type. So I don't know if we caught that in afterwards or not, but that's not right. That should be n-type. You guys see why that should be n-type? Phosphorus is to the right. That should make an n-type material. I assume I just mistyped there, and I hope we graded it correctly. I can't imagine it got past Danny. She catches all my mistakes. This year it's Conrad. He's catching all my mistakes. It says the surface concentration is maintained at 10 to the 20th phosphorus atoms per centimeter cubed, right? So we paint the surface with phosphorus, and the amount that we paint on the surface is 20 phosphorus atoms per centimeter cubed. And we say that it's maintained. So we're assuming that as you dope this thing, what happens when you dope it is you're driving atoms into it, right? So if you looked at the bulk of this semiconductor, this is silicon, right, going into the material this way. But at the surface, we're going to paint phosphorus atoms at it. So if we plotted the concentration as a function of x over here, at the surface, we would have some concentration. We call that our surface concentration. Then x, and we can get a line for what concentration will do as a function of x over time, okay? What we're assuming here is that the surface concentration, let me redraw that. The surface concentration is not changing, right? CS doesn't change over time. If you painted a really thin surface of phosphorus atoms, a real thin skin, then as it drives into the material, you can imagine that this surface value goes down, right? Because they're diffusing in. If that's the case, you have to have a different solution to fix second law. And we didn't teach you how to solve PDEs in this class. That's not a prereq. So we can't solve for that solution in this class. Instead, we have to assume that this is staying constant at the surface. Otherwise, our equation's getting it wrong. Okay? That's all that's saying. It says, okay, it gives us a value at the surface. It says the initial concentration of phosphorus in the material is 10 to the 18th. So we know that right here, it's 10 to the 20th. Deep within the material somewhere, it's at 10 to the 18th, like it was already doped with phosphorus to 10 to the 18th. It's just more at the surface, 2 orders of magnitude, 100 times more. It says, how long should you treat your sample at some temperature if you seek to obtain a concentration of 10 to the 19, 1 micron into the material? So at some position in your material, 1 micron, we want to make sure at that point that we reach 10 to the 19th, okay? So how do you go about solving this? Pramit?
Yeah, so I didn't know that the gradient is nonlinear.
So how do we know that it's nonlinear? Let's read the question again. It says, in a different silicon device, you seek to create, we should have said n-type channels by doping with phosphorus. The surface concentration is maintained at something, and initial concentration is something. Anytime you see that something's being maintained, that means that time is changing. If we say the initial concentration, that definitely is a red flag. This is non-steady state diffusion because there's an initial value which is going to be changing. How long should you heat treat your sample for if you seek to obtain a concentration at some specific distance in your material? None of that is telling me that this is steady state diffusion. This is definitely non-steady state diffusion. It says the diffusion activation energy is given with the pre-exponential. So this is definitely non-steady state diffusion. So because it's non-steady state diffusion, you could say to yourself, okay, because of that, I know how to solve this. I've seen this before. The concentration at any position x is equal to minus x, and then you got the surface concentration minus 0. That's equal to 1 minus this error function of the position x divided by 2 square root of dt. Okay? So this is the equation that if you know enough of the variables, you're going to be able to solve for it. We asked for how long, I think? It says, yeah, how long should you heat treat your sample for? So we're going to be solving for t here. So to solve for t, we need to know everything but t in this. So 1 micron. It gives you information to solve for the diffusion coefficient. We'll write that out in a second. You know what the concentration you're trying to solve for at that position, 10 to the 19th. The initial concentration, 10 to the 18th. Surface, 10 to the 20th. Initial, 10 to the 18th. So you know all of this. What about d? Well, we know for diffusion that the diffusion coefficient, d, is equal to d naught, right? D is equal to d naught multiplied by the exponential of the activation energy for diffusion divided by thermal energy, kBT. Okay? And it tells you in the question where is it? The activation energy, 2.75 electron volts. Because that's given in electron volts, you know that it's going to be K as opposed to R, right? An electron volt is an energy per atom, not per mole. Joules are per mole, basically. So you know it's going to be kBT. And it says the pre-exponential is given. So you know how to solve for d. You could take this value for d and plug it in. You know everything except for t. So this would be a straightforward application of Fick's second law. Make sure that you know how to do the error function from a table, pulling linear values. I saw tons of people not do that correctly on the last exam. That's not going away. That will probably be on the final. So if you didn't learn it, come chat with me and we'll go over how to linear interpolate it. Okay? Let's keep going. How about this one? It says you measure the resistance of a large cylinder, 1 millimeter by 10 millimeters in length. That's 1 millimeter diameter. Okay, so it's a cylindrical resistance of a cylinder. Yeah, so cylindrical. And you get a resistance, okay, 5.85 ohms. What is the resistivity of your sample? How do you go from resistance to resistivity? Well, that's the thing that takes into account geometry. Yeah, at Lennon?
Would that be the resistivity equals RA over L?
Yeah, the total resistance should be proportional to resistivity. The more resistive it is, the larger the resistance. But it's going to get more resistive the longer your resistor is, and it's going to get less resistive the bigger the cross-sectional area is. So this is a straightforward application of that formula. How about this one? It says another sample has a resistivity of 3e to the negative 3 ohm centimeters. So now it's giving you a resistivity. It says, and a Hall coefficient of some number. Calculate the mobility of the dominant carrier in this material. You can assume complete ionization of dopants and that intrinsic carriers are very small compared to those introduced by doping. Report the mobility in these units. So a lot going on in this question. First off, when we say that it's an intrinsic material is far less than extrinsic, oh geez. Okay? Remember the overall conductivity is given by this expression. The conductivity is equal to the number of electrons times the charge of an electron multiplied by the mobility of electrons. This needs to be added to the number of holes multiplied by the charge of a hole multiplied by the mobility of a hole. That is technically the correct equation to describe conductivity. But what have we said? We've said this thing has been doped to such a degree that intrinsic carriers are very small compared to those introduced by doping. So we don't yet know which one of these is the dopant, N-type or P-type, but once we figure it out, if it's N-type, we can ignore this term. If it's P-type, we can ignore this term. That's what that's saying. So now we need to figure out which one's which. The way we do that is, well, we are given a resistivity. We're given a Hall coefficient. So let's go back to Hall and remember what that told us. Hall was in chapter 12, about midway through after this. Here was Hall. Hall measurement, the Hall voltage, what are we given? We're given a Hall coefficient. So we're told what RH is. RH is equal to 1 divided by the number of carriers, your carrier concentration times the charge. Since this is a positive number, we know that this is, nothing here is going to make that positive if P is positive, right? So in other words, we know that this must be positive because N is negatively charged, right? N is, the charge of an electron is negative. So this must be holes. We have holes is our extrinsic dopant. which means in our expression over here, because we know it's been extrinsically doped p-type, we're going to be able to drop that term. Yeah?
So it doesn't matter, so that's the absolute value of E, or are you using the case around that?
The Hall coefficient itself would be equal to a negative number if it was electrons. Since it's reported as a positive number, it's holes. In fact, that's how this measurement works to tell you holes versus electrons. You basically, if you remember this, we talked about it in class, you just create a really basic Ohm's law. You pass, your electrons are going this way because current's going that way, but you applied a field going to it, and as it goes through a field that causes these electrons to drift to one side, that's because this material is predominantly N-type doped. It has electrons. If it was P-type doped, then the holes would drift the other way. So this voltage is going to switch dependent on which material it's been doped with, holes or electrons. Since it's a positive number for our Hall coefficient, we know that this is P-type doped. Okay? This is taking forever, sorry. We'll go a little bit faster just so you can see more examples. How about this one? P-glass. P2O5 is used in the semiconductor industry. Solid P-glass can be created by decomposing PH3, whatever that's called, phosphorus hydride, right, in the presence of oxygen to yield P-glass and a byproduct gas. Anytime I'm telling you and some byproduct or some reagent, it's me telling you I'm going to want you to write the equation. You have to figure out what that byproduct is, right? Say, write a balanced chemical reaction with integers as coefficients. So how do you go about this always? What I always do is, you know the reactor, it says you make P2O5 with this as a starting thing. You start out with PH3 and oxygen, and you're going to make P2O5. So just write it up. Like, write what you know and figure out what's missing. You know that you're going to form P2O5, right, by starting with O2 and PH3. We'll get the coefficients right in a minute. And then it says plus a byproduct gas. So we have a byproduct gas, not a reagent, another reagent. So if you look at this, what's the obvious thing that needs to be over there? It's got to be hydrogen, right? So now it's just a matter of getting the coefficients right. Start with P2O5. We can't change the number of P's on the right-hand side, so we need to increase them over here, 2, right? So now if you've got 2 of these, whatever that chemical is called, that's 6 hydrogens, so we've probably got to have 3 of those. Now our oxygens are the last ones we have to balance. To go from 2 to 5, it's going to be like 5 halves. 5 halves? 5 halves. Right? You have 5 half moles of that. Or you can multiply the whole thing to get integers. Doesn't matter. Yeah, Faraz? You could. I'll have to, and on questions like this, I have to give you credit. If you do anything that's valid, then I have to solve it multiple ways when I write the solution. Water could be the byproduct. I don't know what actually is. How would you figure out which one's the byproduct, actually? Because water, you could write a separate equation where water is the byproduct. You're absolutely right. We could write a balanced equation. How would we know which one actually happens? You learned about it in this class. What do? For this reaction right here, we can write a delta Rg for that entire reaction, right? That delta Rg is equal to delta Rg naught, which means as it's written on paper, right? And then it's this plus RT natural log of Q or K. We've called it different things, but it's basically the reaction quotient. It's products over reactants, okay? So in this case, to tell whether or not hydrogen or water is the byproduct gas, I would have to know all the partial pressures involved. If I don't know that, then all we can solve for is what theoretically it ought to be, delta Rg naught. How do we do delta Rg naught? Delta Rg naught is the sum of the delta G of formations of the products minus the same thing but for reactants, right? So we would look at this, we'd say P2O5 delta GF of P2O5 at some temperature, right, equals some number, right? You could do the same thing for hydrogen, for oxygen, for PH3, and we could say it's going to be 1 times P2O5 plus 3 times hydrogen, which is going to be 0 because it's elemental, minus the quantity of 2 times this PH3 plus 5 half times 0, right? If that's a positive number, then this is not going to happen. If it's a negative number, then it's at least possible that it happens, but you would have to compare that to the same exact calculation for delta Rg naught, but for water. The one that's more negative is the one that will happen. Okay? I'm not seeing enthusiastic nodding. Can I clarify? Yeah, Faris?
You also have to consider the RT natural log Q term.
Oh, hands down. Like in an actual reactor, you have to consider RT natural log Q. But at least on paper, which one should be more favorable, you could figure that out. In some real reactor, you'd have to know the partial pressures to get RT natural log Q term. Okay? So we know how to write this equation. It says what species are reduced or oxidized. Very likely, I will put something like that on the final. Reduced and oxidized, you just remember the old oil rig, right? Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So you could look at this, and you could say, what's changing oxidation state? Well, oxygen is at 0, and it's going to -2. So it has gained electrons, so it's been reduced, right? Meanwhile, H3 went from -1 to 0, so it lost electrons, so it was oxidized. P is in a +3 state here, and it's in a +5 state here, so it went from 3 to 5, so it lost electrons. It was also oxidized. So this is gross. Like, there's a lot going on here. Okay? Then I actually give you pH, I give you the what do you call it, the partial pressures of the different gases so you could solve for the RT natural log Q part of this question. And then I ask about entropy. Okay, so entropy, does it go up or down? Well, over here you've got gases, over here you've got a solid and a gas. Over here you start out with 4.5 moles of gas, and you end up with 3 moles of gas. Solid does not have nearly as much entropy. So you get a feel for what entropy is doing. There's a lot of entropy over here, and there's much less over there. So this is not entropically driven, right? Entropy is becoming more ordered. Typically, things don't like to become more ordered, right, from a free energy standpoint, which must mean that bonding is really picking up the slack for entropy. Since entropy is not making this reaction happen, enthalpy must be. How about this one? It says, roughly sketch a TTT diagram for a Hypo Eutectoid steel composition, labeling each field with the phases present. So to do this one, how do we start it? TTT diagrams tell us the kinetics of phase transformations. Okay? So we know that they typically have a shape that looks something like this. You got the dotted lines, right? And so you had like pure austenite was up here. And then if you went over here, you ended up with perlite. Whereas down here, you ended up with bainite. Down here, you had martensite. How does this have to be modified for a Hypo Eutectoid? Because this is for eutectoid steel. If we redo this now for Hypo Eutectoid, first let's remind ourselves what that looks like. The steel phase diagram. You've got this eutectoid reaction. So this is your eutectoid composition of steel. Down here, you've got a mixture of alpha plus Fe3C. So you've got ferrite plus cementite. Here's your ferrite. Here's your austenite. This is going to be austenite plus ferrite. This is going to be austenite plus cementite up here, pro-eutectoid ferrite and pro-eutectoid cementite. Okay? Hypo means to the left or the right? To the left. So we are at one of these compositions over here. Okay? So what do we need to do to our TTT diagram? Well, before you ever get to this temperature, right, that T alpha beta that we've been talking about generically in terms of phase transformations, before you get to that eutectoid, you've still got a transformation happening. Above that, this austenite is turning into ferrite, right? So if we were to draw the TTT diagram, up here at temperatures above 727 degrees or whatever it is, right? That's where the eutectoid temperature is. We'll just call it TE, our eutectoid temperature. It's not just gamma up here forever. There's going to be some point where you're going to end up with gamma plus ferrite. All right, that's one change you have to make to it. The general shape still is going to look the same, but you're going to have this region where you have gamma plus ferrite, and then you get the rest of the shape. So with the dotted line. Over here, you're going to have alpha plus perlite. Here, you're going to have alpha plus bainite. Here, you're just going to have martensite. Is it clear why this would be the case? Because where's our phase? Oh, we just drew it, right? Our phase diagram, as we cool this thing down, any austenite that turns into ferrite up here, whatever fraction of that happens, is no longer available to turn into perlite. Perlite is when you take this austenite phase, if you were to go right through the middle and it all transforms into that, you get either perlite if it's at high temperatures or bainite if it's at lower temperatures. But if some of this transforms into alpha, then it's not available to turn into that perlite mixture. So instead what we get is a mixture of perlite, but with whatever transformed before that in the pro-eutectoid part of the diagram. Okay? So hypo eutectoid would have this alpha plus P, whereas a eutectoid steel will just have P. Nothing forms ahead of it. If you're hyper, it's going to be the opposite. If you're over here to the right of it, if you're over here, you no longer form above the eutectoid ferrite, you're going to form above the eutectoid cementite, Fe3C. So instead of that, you'll have Fe3C here, plus perlite. Okay? This make sense? Yeah. How do we get information about them? What do you mean? Oh, okay. So by definition, and this is just what we've defined by human definition, how we defined it, we've said if it forms above or below the nose of this TTT diagram is when is the dividing line between perlite and bainite. It's totally an arbitrary definition. It's just what we've decided. In general, what can you say about perlite and bainite? Perlite is thick lamella because it's happening at a high temperature where there's lots of diffusion. Bainite has really thin lamella because it's at low temperatures where diffusion is slow. Okay? Can I answer other questions about this? Okay, let's keep going. Say, explain why is there a nose? So why would there be a nose? To answer that question, you want to go back to concepts we covered in kinetics. A nose means that there's a time, because remember this is plotted against time. It means that there's a time when this transformation happens at its fastest. If it happens at its fastest, that means that the rate has a maximum. So if you remember from class, we showed you the rate of transformation. As you cool down, if we plot rate on this axis, where this is whatever transformation we want to talk about, let's just call it alpha beta. For whatever transformation, there exists a maximum rate, right? At this temperature right here, we'll call that T max. That's when you're going to transform at the fastest rate. Why is that? Remind me, why is that the case? Why is there a maximum? Like, why doesn't it just get better and better the lower we go? Or better and better the higher we go?
It's like the difference between the nucleation and the...
Yep, nucleation. Basically, you get better and better nucleation down here. The number of critical nuclei which are going to be available to start transforming, well, they just get better and better the lower you go. Right? The more you supercool something, the more and more critical nuclei you have. But it doesn't help you a lot to have oodles of critical nuclei that can't grow. Right? So you have to balance having lots of critical nuclei available to grow, but then you have to help them grow, and that's going to happen at higher temperatures because your diffusion takes off. So your attachment rate, VD, is up there. When you combine these two terms together, you get some maximum rate of transformation. Right? That's why there's a nose in the TTT diagram. If you get a maximum rate, you get a minimum time, and that's the nose in the diagram. It says a metal is cooled below its solidification. A group of metal atoms collide together and form a particle, a solid particle with radius r. The atoms then dissolve back into a liquid. Explain why this occurs, citing the driving forces that influence the overall change in energy as it goes solid to liquid. So why does this happen? Why do we see dissolution? They clumped together and they decided, no, I don't like it. Why? What's the energetic reason why that would happen? Yeah. Yeah. In doing so, as they collide together, you all of a sudden have some particle of size r, but in doing so, you had to create all these dangling bonds, right, along that surface. So the surface energy in this case must have been larger than the benefit that you got by some volumetric amount, right? So if r is less than r star, if r is less than some critical size, that will just dissolve again because the overall energy was not negative. Or in other words, the volumetric component, the volume of this small particle, was too small to make up for the surface area. You guys know that as you move towards smaller and smaller particles, surface area gets larger. This is why in your catalytic converter in your car, we don't make the thing out of platinum, right? It'd be crazy expensive. Instead, we put tiny little particles of platinum all over those things because when they're tiny, they actually have a huge surface area. You can get like a whole football field worth of surface area on a handful of particles because they're tiny, right? And because they're tiny, they don't cost you a lot of money because you're not actually putting a lot of volume of platinum in there. This same thing happens here. You get tons of surface area if you have a tiny particle, and surface area costs you energy. So it doesn't happen, it just redissolves again. How about this one? It says, explain why dislocations of the same sign tend to stack up vertically. You guys remember why that was the case? We showed you some videos of it happening. We said in a material, we showed you with the soap bubbles, right? We said that dislocations of the same sign, you can see them in the video, they stack up like this. And if you happen to have two kind of on the same row, like these are on the same row as one another, they repel one another. But if they did something, in this case, they dragged that one down, then they lined up afterwards, before and after. Why is that the case? Why do they line up? Anybody? Strain fields, right? So think of that this vertical line, that represents an extra half row of atoms. So let's draw it. We could say that this represents compression, whereas this represents tension, right? We would say that there is a compressive field, compressive, right? Whereas there's tension here, tension, 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 tension. As much as you can make these red and green overlap, think how great that is. You have compression, which it doesn't like, overlapped with tension, which it doesn't like, but overall, you get like a healed lattice there. So of course they're going to stack up, right? Now it depends on how big this strain field is. If this strain field is, I don't know, like 10 nanometers, but your next dislocation is 100 nanometers away, the strain is already gone by there. So this thing doesn't have to line up because it doesn't feel the strain field, right? It doesn't interact with it. So they have to be a certain distance from one another, which is proportional to the strain field in order to line up like that. How about this? Rank the Young's modulus of ceramics, polymers, and metals. Explain the origin of this difference using a sketch relating energy and force to interatomic separation. So first off, what is Young's modulus? That's the modulus of elasticity. That's the stiffness of your material, right? So, or in other words, if you take stress, you can figure out the strain that you get by multiplying it by Young's modulus, right? It's your constant of proportionality. It tells you how much strain you get for a given stress, okay? So why is it, well, if we rank them, right, Young's modulus for metals versus ceramics versus polymers, which one is which? Which one of those is which? Which ones are the most stiff? From your experience, what's the stiffest material? Definitely going to be ceramics. What about the next one, metal or polymer? Metal, and then polymer. Now, then it says, explain this. It says, explain the origin of this difference using a sketch relating energy or force to atomic separation. Let's do energy first. If we related this to energy, we would say, if this is our energy diagram showing energy versus interatomic separation, R, we know that, let me change colors on these. Let's say this is ceramic, we'll do metal, and we'll do polymer, okay? Polymer looks like this. It's not very strongly bound, okay? Does not have a deep energy potential well. Whereas metals, brown, they are much more so, okay? And ceramics are extremely more so, okay? So why does that lead to a difference in modulus? Modulus, if you remember, modulus was proportional to 1 divided by R naught multiplied by dE dr, the second derivative of energy with respect to radius, evaluated at R equals R naught. So that's kind of a mouthful of math there. What's it really saying? What's the second derivative equal to? The first derivative is it's just the slope at any given point. What's the second derivative? It's the curvature. So at R naught, let's just draw this for this guy for a minute, for the ceramic. At R naught right there, is the curvature a large or a small number there, right? It's a high curvature, right? It has a high curvature, whereas polymer has a very low curvature. So this second derivative is larger for a ceramic than it is for a polymer. And since modulus is proportional to that thing, you should expect to see higher elasticity, a higher stiffness for ceramics than either metals or polymers. Okay? If you plotted this against force, you could get the same understanding, and it makes a little more sense, I think. Force, the same exact drawing, we can put it against force, right? The force diagram looks like this. You've got, so the R naught value is when there's no net force acting on it, right? If it had a net force, it wouldn't be moving. So force must be 0 at R naught. So we're going to intersect that thing like this. That would be our ceramic, right? Now, why does that make it a stiffer material? Well, now look at the slope. Remember, force is equal to the first derivative of energy with respect to R. So dF, so Young's modulus, is going to be equal now, it's going to be proportional to the first derivative of force with respect to R, which is the slope. If you take the slope of this thing, it's a really large number, right? Or in other words, it takes a lot of force. It takes a lot of force, right? The slope is high to get a little bit of strain. To separate these things a little bit takes a lot of force. So it's a stiffer material. Whereas a metal or a polymer, which color was polymer? Polymer is blue. A polymer is going to look more like this with a very low slope. It doesn't take very much force to get a lot of strain for your polymer. Okay? Yep, Fars or Promit? They're not necessarily at the same value. Nope, they're not. I drew them at the same value. They don't have to be at the same value. That's a good catch. Yep.
So like, if we had a question on this, would you want us to like justify why those curves are where they are, or just like memorize them and be able to?
If you just drew it exactly like this, you'd get full credit. I hope they understand it. That a ceramic melts at a higher temperature, it must have a deeper potential well. It must, like, where that comes from, it's a stronger bond. I hope you understand those concepts, and I might ask questions about them. Anyways, that's an example of what last year's final looked like. There was one more question. I'll just at least show it on the video, so if you want to go back on YouTube and go over it, you can see what this was. There was one more question on phase diagrams, so you can get a feel for the type of questions that I ask by reviewing this YouTube video.